Hello everyone. Welcome to this video on how to compute expectation of function of random variables. Here is a specific data science interview question on how to compute expectation of function of random variables. If both x and y are random variables with uniform distribution, what is the expectation of the maximum of x, y? What if we have n variables? Here we assume that all random variables x and y follow standard uniform distributions. That is, x follows u of 0, 1, and y follows u of 0, 1. However, the solution described here is not difficult to be extended to more generic cases. This kind of problem can always be solved by the following 3 steps. The first step is to define the function of random variables as another random variable, and then compute its probability distribution. The last step is to compute its expectation based on its probability distribution. First, we define another random variable z, which is a function of x and y. That is, z equals the maximum of x, y. Here we assume both x and y follow standard uniform distribution. Their probability density function is defined as 1 if x is between 0 to 1, 0 otherwise. Next, we compute probability distribution function of z by first computing cumulative distribution function, shorted as CDF, then calculating its derivative. The detailed steps are described as follows. There are 3 different cases for computing CDF with respect to different ranges of value of z. For any z is less than 0, the CDF is 0, as both x and y can only be valued between 0 and 1. For any z is greater than 1, the CDF is 1, as both x and y are between 0 and 1, which must be less than 1. For any 0 is less than or equal to z is less than or equal to 1, CDF f of z equals to the probability of the maximum of x, y is less than z, which is the product of the probability of x is less than z and the probability of y is less than z, and it equals to z squared. Finally, we can compute PDF of z by computing derivative of its CDF. Like CDF, there are 3 cases for computing PDF with respect to different ranges of value of z. For any z is less than 0, derivative of CDF is 0. For any z is greater than 1, derivative of CDF is also 0. For any 0 is less than or equal to z is less than or equal to 1, we compute derivative of CDF with respect to z and get PDF as 2z. Figure 1 shows PDF curve. After getting PDF of z, computing expectation of z becomes straightforward. Expectation of z equals to the integral of z times its PDF, which equals to 2 over 3. So the expectation of the maximum of x, y equals to 2 over 3 if both x and y follow standard uniform distribution. Now we extend the above solution from maximum of 2 random variables to maximum of n random variables. Here n is greater than 2. Let x1, x2 to xn denote n random variables, and all of them follow standard uniform distributions. The question becomes finding expectation of maximum of all these n random variables. We define another random variable z as maximum of x1, x2 to xn. We can compute CDF of z, which is a piecewise function by the same way as 2-variable case. The CDF of z is given as follows. F of z equals to 0 for all z is less than 0, and 1 for all z is greater than 1. F of z becomes z to the power of n for all 0 is less than or equal to z is less than or equal to 1. Like 2-variable case, we compute PDF of z by computing derivative function of its CDF. Its PDF fz of z equals to 0 for z is less than 0 or z is greater than 1, and becomes nz to the power of n minus 1 for 0 is less than or equal to z is less than or equal to 1. It is also a piecewise function. The final step is to compute expectation of z by integrating z fz of z, which equals to n over n plus 1. So the expectation of the maximum of n random variables equals to n over n plus 1 if all random variables follow standard uniform distributions. That's it. Thank you for joining us.